In this ICFD++ example, we are going to demonstrate collection efficiency calculations using Eulerian Dispersed Phase and using the new Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. In this example, we will set up cases to calculate the collection efficiency on both a circular cylinder and a NACA 21 airfoil. We can see the cylinder example on the screen with the cylinder boundaries and the far-field boundaries. Before diving into this example, I will briefly cover the new features and components of the ICFD++ AUI for first-time users. For a more in-depth understanding of the ICMP AUI features common across all Metacomp software, please click on the ICMP AUI demo link popping up on the left side of the video, or refer to the ICMP AUI section of your ICFD++ documentation. This ICFD++ interface is composed of the menu bar, where the mouse is currently moving, the toolbar, which has shortcuts to the commonly used functions and visualization controls, the canvas, in which the geometry or solution is displayed, in this case the cylinder example, and the notebook, currently showing that you are in CFD++ simulation setup mode. Within the notebook, ICFD++ has its action tree, or setup wizard, which will guide you logically through the various steps of the problem setup and one or more information trees, in this case the groups and boundary families tree, and the boundary conditions tree. Corresponding to each item or step in the action tree, or information tree, is its action panel on the left, where the user is given the relevant choices based upon choices made in previous and current panels. All panels are dockable and resizable. I'll now take a moment to demonstrate the mouse controls. 3 buttons on the mouse can be used to rotate, translate, and zoom. The left mouse button can be used to rotate the grid. The middle mouse button, moved to the left and right, can be used to translate the grid on the canvas. The right mouse button, moved up and down, can be used to zoom the grid on the canvas. The XY button can be used to get back to the default XY view. Let's now set up this case from the beginning. We're going to start with selecting a working directory. By default, the current working directory is listed in the entry. We're first going to start with the cylinder example, which is the cylinder subdirectory in the current working directory. Click OK to select the cylinder directory. Proceeding down the action tree, I'm now going to analyze the grid files and read the BC family file. The grid files are the cells, nodes, and exBCs file, and the BC file is the mcfd.bc file with the BC names. Let's click OK to analyze the grid. The grid information comes up on a panel. The information shows around 29,000 quadrilateral cells in the grid, with 4 boundary selectors. The number of faces on each boundary family are shown, along with the family name. Click OK to continue. This now brings up the Cell Types and Volumes panel. By default, the quadrilateral cell has already been selected based on the information in the previous panel. This selection tells us the valid cell types for the simulation. We can now click OK to continue. We're going to be setting up a general fluid problem, so we can select the general fluid problem, and we aren't going to be using a wizard for this setup. Click OK to continue. In this example, we are going to be simulating water impingement on a circular cylinder and calculating the collection efficiency. The collection efficiency is the ratio of the mass flux of the impinging droplets on the cylinder surface to the mass flux of the free stream, and is an important parameter in predicting the ice accretion. Therefore, in this case, we're going to be simulating 2 phases, the gas phase and the water droplet phase. For fluid type, let's select multiple phases. The secondary phase is for the water droplets, and we're going to treat the secondary phase as a dispersed phase. The primary phase fluid is air, so we'll select gas. And the species content in the primary phase is only a single species for air. We're going to be simulating perfect gas, mostly below Mach 0.5, and the flow is going to be simulated as viscous and turbulent. We're not going to be adding any additional flow physics, and we're going to be running a steady state simulation. Click OK to confirm the problem definition. The next panel brings up additional specifications such as grid motion, co-simulation, and other complex modes that could be used in other simulations. In this example, we won't be using any of these advanced settings. We can click OK to continue. This now brings up the equation properties. In the problem definition, we had selected that the flow would be mostly below Mach 0.5. The interface has automatically selected preconditioning for this reason. There are many turbulence models in CFD++. We're going to select the default two-equation realizable K-epsilon model for this simulation. For dispersed phase, there are two models, the Eulerian Dispersed Phase and the Lagrangian Dispersed Phase. We're going to be simulating this case using the Eulerian Dispersed Phase mode. Let's select the EDP mode. For number of dispersed species, we're going to select 1 for the water droplets with a single size. If multiple particle sizes were to be simulated, we could add additional dispersed species in the simulation. There are additional equations for EDP that can be invoked if melting, solidification, or evaporation and condensation were to be modeled. In this case, we are simply going to be simulating the water impingement on the aerodynamic surface, so we will keep the additional equations for EDP to none. We aren't going to be turning on diffusivity for this case. We can now see the summary that the preconditioned perfect gas Navier-Stokes equations will be solved, and the turbulence simulation type is RANS. Click OK to accept these equation properties. We aren't going to be invoking any additional physics source terms in this simulation, so we can click OK to continue. By default, the SI unit system is selected. We're going to be simulating this case using the SI unit system, so we can click OK to continue. The next panel that comes up is the fluid properties for the primary phase. The primary phase in this simulation is air. Let's select the perfect gas properties and click the Edit button. By default, the species properties for air have already been selected, with information such as the species molecular weight and the Sutherland's law parameters for viscosity and thermal conductivity. The plots for viscosity and thermal conductivity as a function of temperature can be seen on the right. Click OK to continue. We're going to be setting up a base pressure for this case. Let's enter 90,000 pascals and click OK to confirm. The next panel that comes up is for the dispersed species properties, which are for the water droplets. Let's click on the dispersed phase information set and enter some species properties for the water droplets. The species symbol is H2O with a molecular weight of 18. We're going to be simulating liquid particles with an initial particle diameter size of 1.6 e-5 meters. We can keep the maximum accumulation and drag augmentation factors to the default and use the default particle drag law, which is based on Mach number and Reynolds number. The species density is 1,000 kg per meter cubed. Let's click OK to confirm these settings. In the main dispersed panel, there are additional options that can be invoked for various flow phenomena associated with EDP. We aren't going to be using these in this simulation. However, let's change the number density reference tolerance and particle density reference tolerance to 1e-6 for enhanced stability of the simulation. The fluidized density reference values will be computed based on the inlet values. For cases involving EDP generation in the domain, such as condensation cases, we would have selected whole volume. In this case, let's select inlet and click OK to continue. The next panel that comes up is for setting up the initial conditions in the simulation. We're going to be setting up an initialization type for the entire domain with a temperature-based primitive variable set. Let's click the plus button to add a new information set. Click on the primitive variables information set and then click the edit button, and we can input further information. We can already see that 90,000 pascals have been set for the base pressure, so let's enter a static pressure of 0, which is the delta P, and a static temperature of 288 Kelvin. Let's input of x velocity of 80 meters per second. It isn't necessary to enter the turbulence quantities at this time. We can set these later using the turbulence initialization tool. Let's scroll down to enter the dispersed phase values. We can see that the H2O species has been selected for the dispersed phase, and we're going to enter a density of 0.05 kilogram per meter cube for the EDP density, and we're going to set up an EDP velocity of 80 meters per second, which is the same as the velocity for the continuous phase, 80 meters per second. Let's click OK to confirm the initial condition settings, and we can scroll down to review these settings. Click OK to continue. The next panel that comes up is to select the boundary conditions for the simulation. Let's use the right mouse button to zoom in to have a look at the boundaries. In the Groups and Boundary Families tree, we can switch on and off the boundaries on the canvas using the wireframe icon next to the boundary name. The first BC is the cylinder wall, shown here in red. Let's drag the cylinder wall boundary family to the wall boundary condition type. We're going to be selecting a viscous wall with a wall function integration, which is appropriate for this grid. And we're going to be running an adiabatic heat transfer type with 0 heat flux. We're going to keep the wall motion type to stationary. In the lower portion of the panel are the additional modifiers that can be invoked for a wall boundary condition. In this step, it is critical that we select the Extrapolate EDP Velocities selection, as this enables the extrapolation of velocities for the impinging water droplets, allowing them to escape the domain. Click OK to continue. We can now see on the Groups and Boundary Families tree that a green tick appears next to cylinder wall to confirm that the boundary condition has been set. And if we place the mouse next to wall BC1, we can review the settings for this boundary family. Let's now select the far field boundary condition. In this simulation, since the far field boundaries, which are shown here in green, are very near to the cylinder boundary, we're going to be selecting a symmetry boundary condition for this BC. Let's select the default symmetry BC and click OK. The next boundary condition is the outflow boundary condition, shown in blue on the right. Since this is an outflow BC, let's select outflow and drag it to the open BC type. For the outflow boundary, we're going to be selecting an outflow only boundary condition, and we're going to be imposing a condition which is a back pressure. So let's select the back pressure imposition pressure type. Let's add a new information set for the back pressure information. Click on the back pressure information set and click the edit button, and we can enter a back pressure of 0, which is relative to the base pressure of 90,000 pascals that we had set earlier in the species properties. Let's click OK and confirm these settings. The inflow BC is shown on the left in brown. We're going to be selecting a similar condition to what was selected for the initial conditions. For the inflow BC, let's drag this BC to the open BC type. Let's select the inflow and outflow boundary condition subgroup. For the type of information, we're going to use primitive variables, and we're going to apply the characteristics-based condition type. Let's select the existing information set that was used for the initial conditions. We can review these settings here. 80 meters per second for the x velocity, and 0.05 for the EDP density, and 80 meters per second for the EDP velocity. Click OK to confirm these settings. Once again, the turbulence quantities do not need to be initialized at this stage and will be initialized later using the turbulence initialization tool. We've now set up all 4 BCs for this simulation. We can see all 4 green ticks next to the BC names. So let's click OK to continue. The next panel that comes up is the turbulence control panel. We're going to be selecting the default wall function methodology, the advanced 2-layer, with the non-equilibrium wall function type, and keep other settings to the default. Click OK to continue to the next panel. This brings up the turbulence initialization tool. We have one information set, which is for the initial conditions and the inflow boundary condition. We can see the static pressure, temperature, and velocity for this info set. If we right-click on the primitive variables information set, this brings up the turbulence calculator. Let's select yes for is the turbulence length scale known, and input a free stream turbulence level of 2e-2 and a dimensionless turbulence length scale of 3e-3. The free stream velocity is automatically obtained from the info set. We can now click Compute to generate the K and epsilon values, and we can also see our mu-T over mu, our turbulent to laminar viscosity ratio. Click Compute to generate the turbulence quantities. We've chosen the 2-equation realizable K epsilon turbulence model, and these are the K and epsilon values that have been generated based on our inputs. We can also see the mu-T over mu value of 32 for this info set. Let's click OK to add these turbulence quantities to the information set. We can now see these values appear in red for the information set. Additional useful information is shown on this panel, such as the computed density and the computed viscosity in the simulation. Let's click OK to continue. This brings up the Help Set Numerics panel. We won't be needing assistance in setting the numerical parameters, so we can click OK to continue. In the Riemann solver settings, we can keep the default minimum dissipation and click the plus button next to the preconditioning controls to review the preconditioning settings. It is important at this stage to enter an approximate system velocity for this simulation. We're going to choose the free stream velocity, which was 80 meters per second. This information is used by the preconditioning algorithm to determine an appropriate lower bound for the preconditioning parameter based on the system velocity. We can leave the other preconditioning settings to the default and click OK to continue. We're going to be running the simulation from the beginning, so is this a restart can be set to no. Let's enter 750 global steps for this run, with 6 orders of magnitude convergence for run termination. Click OK to confirm these simulation strategy settings. We can now input the time integration settings. We're going to choose to ramp the Courant number from 1 to 200 over the first 100 steps, which is a typical setting for a lower Mach number flow. We can see that the under relaxation for EDP has automatically been set to 0.67. We can keep to this default. All other settings can be kept to the default, and we can click OK to confirm the time integration settings. The next panel that comes up is the spatial discretization panel. We're going to be running in second order, and this is a 2D simulation, so the dimensionality of polynomial can be set to 2D with the XY polynomial coordinates. We aren't going to be adding any advanced settings. Click OK to continue. In the neutral plot file options, in the options for pressure, temperature, velocity, and density, by default the pressure, temperature, density, and velocities are outputted to the solution file. Let's now go to the EDP menu and scroll down and click on the dispersed species properties. And let's add additional variables to be output for the dispersed phase, such as number density, density, x and y velocity, surface area, radius, and collection efficiency. We're going to be calculating the collection efficiency in this simulation, so we'll specify a reference EDP density of 0.05 kilograms per meter cubed, which is the EDP density that we had set up in the dispersed phase. And let's also input a reference EDP velocity of 80 meters per second, which is the free stream velocity. These reference quantities will be used to compute collection efficiency and will be output to the solution file. Let's click OK to continue. A message shows up asking us if we wish to copy the neutral plot file options to the plot options file. Let's click OK to write these settings to the file, and click OK to confirm these output options. The next panel that comes up is the probe and output files, and by default the frequency of outputs is going to be every 200 steps. The next panel that comes up is the probe and output files panel. The probe type is the neutral plot file, which we had selected in the previous panel, and the frequency of output is every 200 steps, so the solution file will be written every 200 steps. Okay, let's click OK to continue. We can now save the input file and choose to run CFD++ in single precision mode using single CPU, and click OK. The simulation has started running in the output panel. It shows some information per time step. The solution files are being written in the working directory, and the results section of the tutorial will explain how to post-process and query these files and calculate the collection efficiency using the solution. We're now going to be setting up the same simulation, now using a NACA airfoil, which can be found in the airfoil subdirectory. Let's click OK to confirm this as the working directory, and select to analyze the grid and read the BC family file. The grid information shows 22,000 quadrilateral cells in this grid, with 3 boundary selectors, the outer, the wing, and the trailing edge. And click OK and we can see the boundary families appear on the canvas. In the cell types and volumes panel, the quadrilateral cells have already been selected as the valid cell type for the simulation. We can click OK to continue. We're going to be setting up a general fluids problem with no wizard, so we can click OK in the general problem definition panel. We're going to be simulating water droplet impingement on an airfoil. So we're going to be simulating multiple phases for the air and the water droplets. We're going to treat the secondary phase as a dispersed phase. And the type of the primary phase fluid is gas for air. And the species content in the primary phase is a single species. The flow is compressible, and we will simulate a perfect gas case, mostly below Mach 0.5. The flow is viscous and turbulent, and we won't be adding any additional flow physics, and we're going to be selecting steady state for the simulation type. Click OK to continue. We aren't going to be adding any additional specifications such as grid motion or co-simulation. Let's click OK to continue. This now brings up the equation properties for the simulation. We had selected the flow to be mostly below Mach 0.5. The interface is automatically selected preconditioning for the solution methodology. We're going to again keep to the realizable K epsilon model and simulate the case using the Eulerian dispersed phase with 1 dispersed species. There isn't a need for additional equations for EDP, as we won't be simulating melting, evaporation, or condensation. And we can keep the turn-on diffusivity to no. The summary shows that we're running a preconditioned perfect gas Navier-Stokes simulation where the turbulence type is RANS. Click OK to confirm these equation properties. Since the boundaries of the domain are fairly close to the airfoil and this is a low-speed flow, we're going to add an additional physics source term for the far-field absorbing layers. Let's click on far-field absorbing layers and click OK. The specific settings for the far-field absorbing layers will appear further into the action tree. We're going to use the default SI unit system. Click OK to continue. We now move to the fluid properties for the primary phase. Select the primary gas properties info set and click Edit. We can see that air has been automatically selected by default. Click OK to confirm. We aren't going to be setting a base pressure in this simulation, so let's click OK to continue. We're now going to be setting up the species properties for the dispersed phase, which are the water droplets. Let's click on the dispersed phase information set and click the Edit button and enter information for the water droplets. The species symbol is H2O with a molecular weight of 18, and we're going to select liquid particles with an initial particle diameter of 16 microns. We can keep to the default factors for maximum accumulation and drag augmentation and to the default particle drag law based on Mach number and Reynolds number. Click OK to confirm these settings. Once again, the EDP is going to be injected via an inlet, so we can keep the fluidized density reference value based on inlet. All other settings can be kept to the default, and we can click OK to confirm. Let's now set up the initial conditions for the simulation. We're going to be selecting again the entire domain with temperature-based primitive variable set. Let's click the plus button to add a new information set. Click on the primitive variables information set and click the Edit button. And let's enter a static pressure of 101,325 pascals, a static temperature of 288.15 Kelvin, an X velocity of 135.6308, and a Y velocity of 11.86616. These initial conditions correspond to a free stream Mach number of 0.4 with the airfoil at 5 degrees angle of attack in the XY plane. Now moving to the turbulence quantities, it isn't necessary to set the turbulence quantities at this time. We'll do that later using the turbulence initialization tool. Now moving to the dispersed phase values, we can see H2O is the species for the dispersed phase. We're going to set up an EDP density of 0.05 kilograms per meter cubed. And we're going to use the same X and Y velocities that were used for the continuous phase. Let's click OK to confirm these settings, and we can scroll down to review the continuous phase and the dispersed phase values. Click OK to continue. The next panel is to set up the boundary conditions in the simulation. We have 3 boundary families in the simulation: the outer boundary, shown in red, the wing boundary, so let's zoom in now to look at the wing boundary, and the trailing edge. Let's zoom in to the trailing edge to look at the trailing edge boundary. For the outer boundary, we're going to be selecting an inflow boundary condition. Let's select the outer boundary family and drag it to the open boundary condition type. We're going to be selecting inflow and outflow boundary condition subgroup using primitive variables, and let's select the characteristics-based boundary condition type. We can select the existing information set that was already created for the initial conditions. Mach 0.4 at 5 degrees angle of attack, with an EDP density of 0.05 kilograms per meter cubed. Click OK to confirm these settings. Let's now select the wing boundary family and drag and drop this to the wall boundary condition type. We're going to be selecting a viscous wall type with a wall function integration, which is appropriate for this grid. And we're going to select an adiabatic zero heat flux heat transfer type with the wall motion type set to stationary. In this step, it is critical to select the extrapolate EDP velocities option in the additional modifiers section to enable the extrapolation of the velocities of the water droplets, allowing them to escape the domain. Let's click OK to confirm these settings. Now the trailing edge boundary family will have the exact same boundary condition as the wing boundary family, so we can simply click on the trail boundary family and drag it to the wall BC type already created. We can now see that the trail boundary appears under wall BC1, and we can review these settings by placing the mouse next to the wall BC type. Click OK to confirm. In the physics source terms, we had selected to activate the absorbing layer controls. We've now reached the absorbing layer's settings. We need to select an information set with primitive variables. Let's select the existing information set. And we're going to be adding the absorbing layers to BC number 1, which is the outer boundary. And we're going to be adding 3 layers, which is a typical setting for a case like this. Click OK to confirm the absorbing layer controls. We can keep the turbulence control settings to the default. Let's now initialize the turbulence quantities for the information set that was already created. You can see the pressure, temperature, and X and Y velocities for the information set, which we used for the initial conditions and the outer boundary. Click right on the primitive variables information set to bring up the turbulence calculator. We're going to select yes for is the turbulence length scale known, and select a free stream turbulence level of 2e-2 and a turbulence length scale of 5e-3. The free stream velocity is automatically obtained from the info set, and we can click compute to generate the k and epsilon values for this simulation. We can also see the mu-t over mu value of 102 for this info set. Click OK to add these turbulence quantities to the information set, and click OK to confirm these settings. We won't be using any assistance in setting the numerical parameters. Let's click OK to continue. In the preconditioning controls, once again, let's set an approximate system velocity for the simulation to 100 meters per second, which is close to the free stream velocity. And we can click OK to continue. We're going to be running 500 global time steps with 6 orders of magnitude convergence for run termination. Click OK to select these settings. Let's ramp the Courant number from 1 to 150 over the first 100 time steps. And click OK to continue. This is a 2D simulation with the XY polynomial coordinates. We aren't going to be adding any advanced controls for spatial discretization. Let's click OK to continue. Once again in the output settings, let's go to the EDP menu and scroll down to the dispersed phase properties. And for the water droplets, let's activate the number density, X and Y velocity, surface area, radius, and collection efficiency. To compute the collection efficiency, we need to specify some reference quantities. Let's select 0.05 for the EDP density, which is what we had used in the dispersed phase. And for the reference EDP velocity, we're going to select the free stream velocity of 136.1489. Let's click OK to confirm these settings and write these settings to the plot output options file. The next panel is the probe and output files panel, and we're going to be selecting the neutral plot file variables to be output to the solution file, which will be output every 200 steps. Let's click OK to confirm these settings. We can now save the input file and run CFD++ in single precision mode using single CPU. Click OK to start running the simulation. The output from the simulation is now printed in the output action panel. You can see some outputs per step. We're going to be explaining the post-processing of files and the calculation of the collection efficiency in the results section of this tutorial. Thank you.